So we left off talking about objects, and the big thing we learned about objects was that was about code reuse using objects, right? So the idea here is that we can have we hate redoing work. That's kind of thing that everybody hates to do, and programmers especially hate it. So the idea here was that we made an animal kind of superclass. Okay, and the idea is that it was a class that represents all kinds of animals. We could build an animal, give it a default name of Andrew, or its constructor could be used to build an animal of any name. And then it would be able to, we could tell it to eat a thing and move. But because it's an animal, we don't know what kind of animal it is, so we just simply said it ate the thing normally and it moved normally, right? So what we did is that we built a reptile, and we initially just built it like this. We gave it its own constructor, and then we showed that basically we'd have to copy paste basically everything from animal and then change what we wanted, and that seemed a bit tedious. So instead, we showed that basically we could establish an is-a relationship, right? There's two relationships objects can have with each other. The first is a has-a relationship. For instance, an animal has a name. An animal object has another object that describes it, right? An animal has a name, right? A ballpoint pen, if we consider that as an object, it has a tip. It has a color, right? Those are things that, so that's one type of relationship that we can establish. The other type of relationship we can establish, so I'm not screaming, the other type of relationship we can establish is a is-a relationship, is-a. So a reptile is a animal. A circle is a shape. Now we know that a circle is a shape, but we didn't codify that into our code, so to speak, right? Here we're going to learn how to codify, put that into our code. And we do that with the extends keyword. Now you can only extend one class, all right? And for reasons we'll get into. You can only extend one class. So we can only establish an is-a relationship with one thing. So we can say a reptile is a animal. And as a result, reptiles have all the things that animals have. They have the string, name, they have a size, they have a color. They don't get the parent's constructors, though. That's the one thing you don't get. And we'll get into that today as to like the headaches that can cause. But it's just a headache only if you're unaware of it. And then reptile gets the eat and the move method. And then we showed we can do something called overriding, right? So we wrote our own, so reptile extended animal, right? We said that a reptile has its own name, right? It has its own constructors. Reptile gets the default name of Ralph. And then we overrode the method here. Notice that it has that my IDE creates a symbol over here that says it overrides the method in animal. And in the IDE, it also created a symbol here to say that that this method was overridden. This means that reptile redefined its behavior, right? Because reptiles, we can say a bit more about how they eat. They most likely crunch on stuff because of just the way they've got mouths and jaws and stuff, right? So when we run this code, we can create a new reptile. Its name is Ralph, and we call r.eat on some lettuce. So Ralph ate some lettuce with a loud crunch, and we got that information here. We built it with the information here. But when we moved it, right, there was no move method in the reptile class, okay? There was no move method. Where's the move method? Well, we said this is an animal, right? So it looks at and says, there's no move method in reptile. But there's a move method in animal, and a reptile is an animal, so we can use that one. So Ralph, the reptile, moved generically, right, because he's a animal. Similarly, we don't have a name variable here, or a size, or anything, or a color, right? We don't have any of that. But that doesn't stop us from, using those variables. Like this.color is equal to new color this.color is equal to color.green, right? Say that this animal is green. nothing stops us from using those variables that we get from animal. Okay. The other thing I mentioned is that if you don't extend if you don't extend a class, okay, Java automatically extends one for you because it wants to make sure that all the classes you write are objects. So if you don't put an extends, Java automatically puts one in for you that it says it extends object. And this is why when you build your own object and you go, object dot, you get all the methods and variables you have, but you also get stuff like clones, equal, toString, notify. These are all important things that you'd want from an object to do. All the things that Java needs to have objects work. And by enforcing that that all objects are in fact objects, and all objects share this common code, it allows you to always make sure you can do this. System.println A, right? This code will always work, right? Animal, right? And it called the toString method over here, right? Because all objects have a toString method. And then if you want something more specific, you can override it. Now let's get into some other things that we need to do. The first thing is that notice that I didn't have my private variables like I said you should always have, right? So, and this was because if I set these things to private name, private double, private color, I get an error over in Reptile because it says that the name is private to animal and the color is private to animal, right? Private means that no other class but me can see this stuff, right? Private means no other class than me can see this stuff. But we don't want it to be public because public means that everybody can see it. And not having a modifier there means that everybody in my package can see it, but I don't really talk about that too much. So realizing this headache, Java has a third keyword. So there's public and there's private. And then there's one more, protected. And that means that I can see this, but also anybody who's a subclass, anybody who's a child class can see this. So this means now that Reptile can see this, but any program outside of anybody who's not in the inheritance chain, in other words, anybody who's not an animal can't see it. Okay, so we've got public, we've got private, and we've got protected. Protected means private to the family, essentially, right? Private means private to myself. Protected means private to my family. Me and my children, and my grandchildren, and any other descendants. So how deep can this go? Well, we can create another class. So let's create a lizard. Okay, so a lizard, right, is a type of reptile. And let's make another class that will do as well. Let's see. So we've created lizard and snake, which are both types of reptile. Now remember, you can inherit only one. You can only have one parent class, right? You can only have one superclass, as it's formally called. In other words, you can only borrow code. You can only reuse code from one parent class. But a parent class can have as many subclasses. A superclass can have as many subclasses as it wants. So, right, because there's many things that are reptiles and there's many things that are animals, right? So in this tree, all lizards are reptiles, and because all reptiles are animals, all lizards are animals as well, right? That makes sense, right? That hopefully makes sense to everybody. And because all animals are objects, all lizards are objects too, right? It just kind of make, I'm using actual examples here rather than proofs, bars, and bosses because this kind of classification that we use for animals makes sense. So let's look at lizards, right? We got to make our own constructor. So I'm going to show what happens when we don't have our own constructors, okay? But I'll create a public static void main just for, again, I'm keeping this mains inside of the classes, turning the classes kind of into programs just for simplicity. We can make a constructor because remember, if you don't have one, Java makes one for you. Okay, so none of that code failed to compile, even though we don't have a constructor, we don't have a move method, and we don't have an eat method, right? So first off, eat, well, that's going to come, well, we have our parent class, reptile, has an eat method in it, and up in the chain in animal, we have a method, move, right? So we've inherited the move method and the eat method, so we don't have to write our own. And we get a constructor for free that Java writes. So let's see what happens. It writes that Ralph moved generically, and Ralph ate a tasty grub with a loud crunch. So why am I getting the name Ralph? So let's experiment a bit. Public. Let's make a constructor, right? Java, when you don't provide a constructor, it provides one for you automatically. So I'm just going to do nothing here, okay? This is what Java automatically generates. So let's run it. Ralph moved generically. Ralph ate a tasty grub with a loud crunch. I'm running the right class, by the way. So where is it getting Ralph from? Well, it turns out there's a bit more going on here in your constructor than you are aware of. So that brings us to a new keyword that you're very rarely going to see, but you want to know it exists. And that's the super keyword. Super, short for my superclass, my parent class, right? So actually, when Java generates a class for you, it doesn't look like this. It looks like this. In fact, in every method, in every constructor, there's an implicit super call, right? Lizard doesn't know how to build itself. It's got to ask its parent. We don't know how to allocate memory and stuff like that. We ask our parent, right? Animal doesn't know how to create memory for itself, so it asks the object class how to do that. So there's always this implicit super call to the parent that kind of just goes all the way up the chain. So super means I call my parent's constructor, right? And so now, if I do, so this, because it's super with no parameters, it calls the parent constructor with no parameters. So if I change this so that it does take in a parameter, watch what it does. Lizzie moved generically, and Lizzie ate a tasty grub with a loud rock. It moved it, it called my parent's parameter, sorry, my parent's superclass, called my parent constructor that takes in a single parameter. So called this over here and passed it into here, and it set the name equal to the name. Now you only are going to ever have one super call. You can't, super only ever happens once, and it must be the first statement in the constructor body. Right, so if you're explicitly calling super, it has to be the very first thing in the constructor. So, as a result, we don't really use super too much. We just simply know it exists, but it's a way also to call your parents' methods explicitly. So we'll see how we can manipulate that a bit, but let's see. So super Lizzie, right? So we can also make a public lizard. So now let's see how this works together. So if I don't provide a constructor now, if I don't provide a name now for my lizard, it will call this.name, this with no parameters, it will call, so the constructor with no parameters will call the constructor with a single string parameter and pass Lizzie to there. And that one will pass it to its parent class and use the code in there. So we'll set up the lizard. So if I don't pass anything in, it will set up the lizard class with the name Lizzie and a green color. If I pass in the name, it will set it to that name and set up the lizard with the green color. And now if I do lizard, so now if I do Liz instead, I run it. Liz moved generically. Liz ate a tasty grub with a loud crunch. Okay. So super means I can call my parent class, essentially, to do stuff from there if I want to really reuse their code for some reason. Okay. Public. So let's go ahead and override the eat and move methods. So lizards, they move in a specific way. They don't just, move around. They scurry. That's the way you would say a lizard moves. So, so I would say this dot name. I could also do super dot name, but it's better to do this dot name. Scurried out of the way. And then we can do a public void eat string thing. So we can override the eat method from our parent, because lizards, they're ambush predators. So they'll pounce on stuff. This dot name plus pounced on blank and gobbled it down. Okay, so now if we run this, we've overridden our parent's behavior. Liz scurried out of the way. Liz pounced on. Oh, I forgot to put plus thing. I don't do this dot thing because there is no thing instance variable. There's just a thing local variable. So Liz scurried out of the way. Liz pounced on the tasty grub and gobbled it down. So similarly with the snake class over here, we'll do something similar, right? We can do a constructor. And remember, these things are pretty simple, so that, to the point that your compiler can probably do it. So generate a constructor. Sam the snake, and let's go ahead and override the eat method, right? This dot name plus the reason why I'm making all these examples of how to override and stuff using inheritance will become clear when we talk about polymorphism in a bit. This dot name, let's see. So snakes engulf things when they're done, hunting it. So this dot name plus engulfed plus thing, and then public void. And how do snakes move? They slither. So let's put that behavior in. So we're going to override our parent's move, right? Rather than using our parent's move, we will say this dot name okay. So now let's go ahead and make a new snake. And then I'll show the last thing with that you can, one of the more useful things you can do with super. Snake s is equal to new snake s dot so s dot, let's see, s dot move s dot eat. Okay. So if we move this, if we run this now, we would get Sam slithered, Sam ate, Sam engulfed something. Let's see, where am I getting that? So print out this dot name. Oh, I see. Our eat method called soup. We want to do. I messed up there. I wasn't paying attention to what I was filling in. Sam slithered, Sam engulfed something tasty. Okay. So other interesting thing you can do with the super method, with super, is you can call your parents' methods. So for instance, in move, I can put in super.move. And now if I run it, it will go Sam moved generically, and then Sam slithered. Right? It will call my parents' method. So super.move will call the move all the way up in animal. Why not all the way up in reptile? Because reptile doesn't have one, so we find it in animal and we execute it. And then it will execute the system.print line. So it will say move generically, then it slithered. So you can use super to call parent methods that have been written if you really need to refer to them again. All right, so that's cool and all. So we can reuse code, right? But does it get more powerful than that? And the answer is yes, it does. So that's inheritance. And this all goes together with the final idea we have called polymorphism. So new, new class animal driver. So this will be the class to show how polymorphism works. All right. So the idea here, let's go ahead and create a public static void. The idea behind polymorphism is that if a reptile is an animal, we should be able to treat it like an animal, right? Suppose you have like a method here called the feed method. Public static void feed, which takes in an animal and a thing you want to feed the animal, right? Now, it would be really annoying if I had to make, a method for each type of thing. So to feed an animal, I would need a method. To feed a reptile, I would need a method. To feed a lizard, I would need a method. That would be really annoying if I had to do that. But however, we've established that an animal, that basically, a reptile is an animal, a snake is an animal, a lizard is an animal. So what we can do is that we can just write one method that uses the superclass. So we can go a dot. My mother called me. All right. So we can write a single method that does all this. We can go a.eat food. And now, let's create a new animal. Animal A is equal to a new animal, right? And just to show you that it is an animal, we can have him move first, right? And run it. Oh, what am I missing? Oh, I forgot the constructor symbol. A dot. Okay, so we've got a dot move. And now if we do feed, a food, it'll run the eat method for animal. Oh, we need a food, so let's go with a cookie, right? Andrew moved generically, Andrew ate a cookie normally, okay? But what's really interesting over here is that I could do this. I can do lizard L is equal to, I can do lizard L is equal to new lizard, okay? And then I can pass in L. Now L is a lizard, right? And this is a method taking in an animal, but it will run all the same. And watch what it does. It says, so see, it did Andrew move generically because I had Andrew there, so let's copy that out. Lizzie pounced on the cookie and gobbled it down. Now look at that. It's a lizard. We passed it into a method that took in an animal. And then when we called animal.eat, it used the lizard method. Now that seems slightly confusing, but let's think about how this works. This lizard is essentially getting put into an animal box, right? A box that can hold any animals. We open the box to feed it, right? And we inside the animal box, we find a lizard. So it eats like a lizard. Okay? So this is called polymorphism, where basically we can write one method or one variable that holds any kind of animal that we want, right? And when I mean that we can do something like this. Animal A is equal to a new lizard. Well, that looks a little interesting. Right, and if you've been looking around online for code, you might have seen stuff like this. List L is equal to a new array list, right? You might have seen this if you were looking around code for code online, and you found out about array list, and you might have seen something like this. List L is equal to new list. Sorry, list L is equal to new array list. And this is called polymorphism, right? And I'm actually going to have to, whoops, what happened there? I'm going to have to use the, the whiteboard very shortly because I like to draw this. So the idea here is that when we create a variable, right? When we create a variable, we give it a name, right? And the variable we created was an animal A variable, which meant that essentially we called it A, that's the label for it, and then we put a label on the box saying what kind of things this can hold. And we said it is a box that holds animals. Now in reality, what we're putting in there is a memory location. It's important never to forget that. We're putting a memory location. It's kind of more of a portal box than an actual box. But that's beside the point. Okay, the idea here is that this is a box that can hold any animal. So it makes sense it can hold an elephant, right? Right, because that's a type of animal. But it also makes sense that it can hold the lizards that we created, because lizards are reptiles, and we've said that reptiles are animals, right? So it can hold any reptile, it can hold any lizard. So when I say animal A is equal to a new lizard, that works because this is an animal box. It's a special box, industrially produced, that holds any type of animal, right? The flip side is that it doesn't work the other way around, right? If I create a lizard box like this, lizard L, okay, just like this creates a new box that's essentially a new variable that we say it's of type lizard. It only holds lizards, right? Then the name L, and then if I go L equals new animal, well, that's just not going to work, right? Because you're saying I want to take an animal and put it into the box. But not all animals are lizards, right? All lizards are animals, but not all animals are lizards. Or to put it more, in a more physical sense, right? That lizard could be Eddie the elephant, right? And Eddie the elephant is not going to fit in a lizard box, right? Lizard boxes are typically small, right? I don't know if the Komodo dragon is a lizard, right? But let's assume for the sake of argument it is. That's only, about man-sized at the biggest, right? And elephants are much bigger than Komodo dragons, so it's certainly not going to fit in an animal box, right? Right. So while you can use a more generic container, you can't use to hold a specific animal. You can't use a more specific container to hold a more general animal, right? So in other words, you can put lizards into reptile boxes, but you can't necessarily put all reptiles into lizard boxes. And as long as you think of it that way, it does make sense. So here we created a new lizard and put it into an animal box. And now a common misconception is that, like, as a student, you might think, okay, so right, if I do lizard a.eat now, a cookie, you might be thinking, okay, so it's going to eat it like an animal because it's in an animal box. But remember, it's just the box. The box that holds things is not the thing, right? This is just simply storing the memory location, right? As soon as we get to this dot, we kind of open the box up and look inside and say, ooh, it's a lizard, cute little lizard. Let's feed it a cookie, okay? So it eats the cookie like a lizard. It does not eat it like an animal, right? You open the box, you see what's inside of it, and you go, okay, that's a lizard, so I'm going to feed it like a lizard. Does that make sense? Similarly, if I were to put a reptile in there, instead of an animal, we run it, and it will say, Ralph ate the cookie with a loud crunch, because that's how reptiles eat cookies, right? We put a reptile into the box, we open, and then once we go to feed it, that's the way it will work. Now, you might be wondering, okay, so why are we bother doing this, right? Okay, so I can see the point of a method, but Well, the answer is, well, what if a lot of times you're not dealing with one thing, you're dealing with collections of things, right? So let's deal with, and we've been dealing with, now in data structures, you learn about how to make collections of things. That's what the next class is, how to make collections, okay? So the idea here is, if we want to make collections of things, and of all sorts of things, we want a way for them to go to be useful together. So let's make an array of animals, a collection of animals. Let's call it a zoo, right? That makes sense. And let's basically create 10 cages for animals. It's always useful to reframe these things, right? So 10 boxes to hold our animals in. Okay. So in box 1, we're going to hold so in index 0, let's go ahead and put animal, just an animal in there. Eddie the elephant, right? And then in index 1, we'll put a reptile in there. And then and now that's pretty cool. We can mix and match what we're putting into each thing, but it makes sense because we're putting animals into these things, right? I can't put a new scanner into this thing because a scanner is not So first I have to import scanner naturally, right? But a scanner is not an animal. It requires a type of animal, and a scanner is not an animal. So new lizard, and then zoo, we'll put in a new snake. And then let's add in one more animal. So our zoo is half full. Let's do animal. Ozzy the orangutan. And now we can essentially rewrite this feed method so that basically we take in a bunch of animals and feed them all food. So let's go ahead and do that. So for int I is equal to 0, I is less than animals.length, I plus plus, animal A, so a single animal is equal, we're going to grab out each animal. So we're going to grab out that individual animal, and then we're going to do a.eat. Okay, so we're going to feed them. So now we are going to feed our zoo, every animal in our zoo, a cookie. Okay, and we're going to get an error, but that's okay. So we had Eddie the elephant, because he's an elephant, he didn't have it. He's an animal, he doesn't have anything specially defined for him, so he just eats it normally. Ralph the reptile eats it with a crunch. Lizzie pounced on the cookie and gobbled it down because she's a lizard. Sam the snake engulfed it, and then Ozzy the orangutan ate it normally. And then we had a null pointer exception because we tried to feed a null a cookie. So we add one more thing. So we grab animal A. If A equals null, I'm going to put in a word here called continue, right? So continue is the opposite of break. Break, what that would do is that it would stop the loop immediately, right? Whereas continue simply says, I'm going to just stop this iteration of the loop and go on to the next iteration. So I was at I is equal to 5, so I'll go to I is equal to 6. So if it's null, we're going to just skip that animal. So all the animals eat, and we're done. So that's polymorphism. It's polymorphism is a word that means many forms, but I mean it is a it's not exactly the most it's a big word. It just means that you can basically treat objects as other objects of the same type, which is a very useful thing. So let's go ahead and go to the slides and see what else they have to say on the matter, right? Because they're useful as a second example. Now, they like to use the law firm analogy by saying, like, each of these, like, we have an employee superclass, and all these employees have different rules, and each type of employee has specific rules. So let's go to documents, slides. Right? So remember, you can graph out these inheritance hierarchies, by the way. Let me zoom in here. right? Like a figure, it can, like you can have a pentagon, which is a type of polygon, which is a type of closed figure, which is a type of figure. You can have all these different types of classes and define relationships like that. So let's go about and think about how we can like program in employees. Like employees work 40 hours a week. They make 40,000 a year, but legal secretaries make 5,000 extra a year, and marketers make 10,000 extra per year, so 50,000. All employees get 2 weeks of paid vacation, but lawyers get an extra week, so for 3. And if you're applying for leave, all employees should use the yellow form, but lawyers will use a pink form. Each employee should also have a specific type of behavior, right? Lawyers need to know how to sue, marketers have to know how to advertise, secretaries take dictation, and legal secretaries, which are a special type of secretary, prepare legal documents. So this is kind of your generic employee. 40 hours a week, $40,000, get vacation days, 10 days of paid vacation, and yellow using vacation form to apply for leave. So now if we make secretary, it would look something like this if we didn't use inheritance, right? And we'd reuse basically a heck of a lot of code, right? We'd actually use all the same code. The only thing that we would change is that since secretaries need to know how to take dictation, they have to have a method that does that too. So if we use the extends behavior, the extends keyword, to make employee a superclass of secretary, because remember, a secretary is an employee, then all we have to do is, instead of having that big class, we can make public class secretary extends employee and just add simply the method there. Lawyers get an extra week of vacation. They use a pink form for leave, and then they have a second method. So we override the methods we want to override. So we extend the employee, and we just override the get vacation form from yellow to pink. And we override the get vacation days to 15. And then we add the sue method. Same thing with the marketer. Then we can have these things chained together. A legal secretary extends the secretary class. So suppose though we got a company-wide change. So this is another reason why we like using inheritance. Suppose you get a company-wide change. Everybody's given a $10,000 raise. That's pretty nice. So the base salary is now 50. Legal secretaries will now make 55,000, and marketers make 60,000. So now we have to go through all the code and change that. But if we modify it, so we change employee to be 50,000, but we're not finished there. All the subclasses still need to be changed. So we'd have to change the legal secretary and the marketer. So instead what we'd want to do is we'd want to use, our parents' information. So this is where super becomes useful. We could say, okay, a legal secretary makes 5,000 more than a secretary. So we'll get the amount a secretary, the base salary for a secretary, and just add 5 on top of that, $5,000 on top of that. So double base salary is equal to super.get salary. That will get the secretary's salary, and then we'll return $5,000 on top of that. So lawyer, right? Lawyers have 5 more vacation days than everybody else, so we'd say get vacation days and add 5 to that. And marketer, which makes $10,000 more than the standard employee, would get the salary of an employee and add $10,000 to it. So let's see how they go into these. So let's go ahead and see basically about how they use constructors. So right, and remember this is going to go into more detail about how constructors and inheritance works, right? So imagine that you get more vacation days the longer you're with the company. So if you work a year, you're going to add you get 2 more vacation days. So when you're an employee is constructed, we'll pass in the number of years that the person's been with the company. So we change that private int years. If you're an employee, we construct you with the amount of years you have, and your vacation days are equal to 10 plus 2 times the number of years you've worked. But if you try to create a lawyer, that's just not going to work. Right? Once you write a constructor that requires parameters in the superclass, you have to write constructors that for employees in the subclasses. That's the short explanation. The long explanation for why you need a constructor is that constructors are not inherited. So all subclasses get the default constructor, which is public, lawyer, super, which will call the employee constructor. So lawyer would call the employee constructor, but the employee constructor does not exist because there's only one constructor for employee, which takes in the number of years. That makes sense to everybody so far? So it's trying to call in a constructor that doesn't exist. So once you add a constructor with parameters in the subclass, you need to add constructors with parameters in the superclass. Once you add a constructor with parameters in the superclass, you need to add constructors with parameters in the subclass. So that's all we really need for this. All right, so we pointed out that all classes are objects. So that means we can also make object variables. So the object class has a whole bunch of methods. The only ones you really need to worry about are equals and toString. In 2168, when we talk about hash tables, we'll talk about the hash code, but that's about it. The other stuff, a lot of it has to do with like multi-threading, but otherwise, really, equals and toString are the big one. ToString is, that represents, as I mentioned, the string representation of an object. And equals checks if two objects are equal to each other. All right? So let's say we're using the point object that we made before. You can store any type of object in the object class. So you can make object 01 equal to new point 5, comma 3. Let's go ahead and actually, I'll show that with our animals because we've just made our animals, right? So we've made our animals. Not only could we put animals there, we could do object A is equal to a new animal. That makes sense, right? Because an object is a superclass for everything. Okay? But the minute we do this, but if I do this, A dot, actually that should be object O. Really? O dot eat. Or sorry, O dot move. That's going to give us an error. The error it says is that it cannot resolve O dot move. No candidates found for the method O dot move. And if we try to run this, it will crash. Cannot find the simple O dot move in an object. Now this is where the whole label concept on those boxes is important, right? Java allows you to store anything in an object, right? And it's not really sure that, and all it can guarantee about what's in the box is that it's got an object and it has all the methods an object has. In other words, it has toString and it has the hash code method and the equals method. It can't guarantee that whatever you put in the box, has the eat method because objects aren't necessarily animals, right? It's possible that there's like 100 lines of code in between this, right? A bunch of code over here, a bunch more code over there, right? And I could do something like O is equal to a string, right? And, now that object's a string, it certainly makes sense that the move method doesn't compile or it doesn't work. Okay, so what this is, it is, right? So, let's see. So we'll get into this in a second, but, so in anything that's an object variable, you can only use the stuff that objects know how to do, which is toString, right? If you're putting a scanner in an object, you can't use the .length method. If you're putting a string in an object, you can't use the .length method. And if you put a scanner in an object variable, you can't use the anything that's unique to a scanner. You can write an object that takes in, and you can write a method that takes in an object, and that can be useful if you're checking if something's null. So let's remember that basically that now why is this useful? That this having this whole object thing with the dot equals. Remember, we've had trouble if we use double equals on two methods, right? If we use double equals, it compares the references. It compares what's literally inside these variables, which is the references. It only produces, it's only true if there are two, if point 1 and point 2 are the exact same object. So here, if we create 2 points at the same location and use double equals, it'll return false. The dot equals method, it compares the states. So if string 1 is equal to string 2, it will print out, if string 1 and string 2 are strings, it will compare them and say, hey, they're equal. But if we write a class and don't have our own double dot equals method, then it will act just like essentially the dot equals. Essentially, let's see. So let's go ahead and create animal. So let's go ahead and go back to the animal driver. We'll create animal A1 is equal to new animal. And animal A2 is equal to a new animal. Assuming I remember how to type. So if I do, so let's go ahead and print out A1 equal to A2. That'll return false. Sorry, that'll print out false. And if I do dot equals A2, that's also going to produce false. Right? Because even though they've got the same name, Java's looking at the references. If I don't provide a equals method, right, in animal, right? Well, I didn't write one. So where's it getting the dot equals method? It's getting it from object because all animals implicitly are objects. And the equals method written inside object uses the double equals because it needs to know how to compare two objects, and the default way is to compare their references against each other. So what you'll do is that you will override two methods. So let's go ahead and we can override that method. So public. So let's write our own equals method. Public Boolean equals, and we'll want to compare two animals to see if they're equal to each other, right? And we'll say they're equal to each other if the names are equal. So if this dot name dot equals a dot name, return true. Else return false. So now if I do this and run it, I get false. Animal A. Let's see. If this dot name dot equals animal dot name, all right, we're still getting false. I wonder why that is. Let's go ahead and be more explicit. Animal A, and let's also give him the name A. Run this. Okay, it produces true at that point. Okay, because they have the same name. Don't know why it wasn't producing it earlier. So let's go ahead. So that seems like it'll work. But what if I do something like this? So that's going to work because even though our method says down here, it says that I'm going to take in an animal A and compare the names. Well, I've got another method actually. The method it doesn't say I'm overriding my parent's method. My parent's method doesn't take in an animal. It takes in an object. So now I'm overriding it. So notice that I now have two methods that have the same name, but different parameters. One takes in an object and one takes in an animal. Now, when you have a method that has two methods that take in the same name, that have the same name and the same number of variables, but they're different variables, or have maybe different number of variables, this is something called overloading. So in this case, right, if I'm comparing to a string, an animal to a string, I want it to return false. So if it's not an animal, I want it to return false. So let's go ahead and see that. If object, was there a way for me to check if object is an animal? There is. There's a keyword called instance of animal. So if it's an if object is not an instance of animal, return false. Else, we'll call our own equals method on an object. But we need to use the right one, so we're going to cast it into an animal because we now know it is an animal. And so now that'll return false. And now if I do A2, it'll return true. And if I pass in a new reptile by the name of A, it's also going to return true because a reptile is an animal, right? So they'll compare like animals. They'll compare their names, and they'll say, ha, A1 and that new reptile are the same animal because they share the same name. Right? So we can check if something is a so we can you check if something is a type of another class by using the instance of method. So here's some examples of the instance of being used. So here, variable is an instance of type. So say we have a string S and a point P. S is an instance of point. Well, a string is not a point, so that's false. S is an instance of string. That's true. S is an instance of P. The point is a point a string? No, it's not. Is point an object? Yes, it is. Is string an object? Yes, it is. Is null a string? No, it's not. And is null an object? No, it is not. So that's how we basically create those things together. All right. So that was kind of a lot to take in, right? But hopefully not too much, because honestly, you don't use these things necessarily too much. They're simply things that have been baked in and written in Java to make programming get a bit easier. So let's see, what can we do now? I think I want to try something for the remaining, we have 20 minutes in class. So, let's go ahead. Yeah, I'll come back with something interesting to do on Monday. But let's go ahead and talk about the last topic in this chapter, and then I'll come back to the slides. Let's go back to our shapes, which is we're going to go back to a new thing. So if you've been looking through your stuff, you might say there's a class here, but you may have also noticed that there's something called an interface. How do you make an interface in Eclipse? In here, I wonder. New. Well, let's go ahead and just create a new class. Shape. There we go. Oh, that's not what I wanted. New class shape. And it says kind. And if I drag down, there's something called an interface here. So interfaces are a second type of class, a new type of class, essentially. They are very interesting types of classes. And you're like, oh God, with a name like interface and it's completely new, it's probably like the most awful hard thing in the world. And it turns out like interfaces are actually ridiculously easy to deal with. Interfaces are kind of really easy. So suppose we're writing a program that deals with shapes. All shapes have, like circles, rectangles, and triangles, have some kind of common behaviors. You have a perimeter, right? Which is the distance outside of the shape, and an area, which is the 2D area that shape takes up. Every shape has a area and a perimeter, but it goes about them in a completely different way. There is like no generic way to compute a perimeter and no generic way to compute an area. Well, not an easy way, at least. Not an easily programmable way. So we can't like make a shape superclass and define a perimeter and an area in a way that makes sense, because if we try creating a generic shape, we won't have a way to like actually compute their shape and area, right? Rectangles, their area is their width times height, and their perimeter is, twice the width plus twice the height. Right? You have two H's and two W's, you add them together. The circle's area is defined by the radius, and the area is 2 pi r, and its perimeter, which is called the circumference there, is 2 pi r. Sorry, pi r squared here, 2 pi r. And a triangle has the area of, well, it's 1/2 base time height, but if you aren't keeping track of the base time height, and you just have the three sides, it's this formula over here, which is the square root of s times s minus a times s minus b times s minus c. And the perimeter is all the three sides added together. So we'd like to write a shape class that basically to say that all these things are shapes, but all these things need to define their own behaviors, right? They can't rely on their parent to have written them for them. Right? So we'd like to be able to, and we'd like to have a shape so we can have like an abstract shape method, so we can use polymorphism to draw all sorts of shapes, and we know how to do it without having to like make a special, method for every specific shape. And the way we can do that is using an interface. So inheritance gives you an is-a relationship, and it shares code. Interfaces give you an is-a relationship, but it does not give you any free code. So you create it. So it's analogous to the idea of roles and certifications, right? I'm certified as a CPA accountant. That means I know how to do taxes. I can do auditing. I can do consulting. These are all the things I can do because I have a certificate. I have a certificate that says I'm a shape. That means I know how to do. It says the triangle. That means I know how to compute my area and I know how to compute my perimeter. So the way we make it a interface like this is you simply list it's really easy. You simply list all the methods that a shape needs to have. If you're a shape, you need to have these methods. So if you're a shape, you need to have a perimeter method. So public double get perimeter. And that's it. That's all you have to do. Right? Notice that I ended it. I didn't have this there. In fact, if it's an interface, it screams at me that's an error right here. What's the error? At a return statement, return 0. It's screaming at me right here. Interface abstract methods cannot have a body. If you've got a method inside an interface, you can't have the curly braces. You have to end it like this. You just simply list all the things that a shape needs to have. Public double get area. So you can only put two types of things in a interface. You can put method headers. And you can't even have variables here, normal variables. Like you can't even like have a string name for the shape. It says that it might not have been initialized, and it also says let's see. Oh, but you can't do that in that. Sorry. Really, the only thing you're allowed to put in there are final variables, like public, static, final, pi, 3.14159. So those are the only things that can go into interfaces. Okay, and so now we go to our circle shape. And when we want to say that a circle is a shape, then here's what we have to add. We don't use the extends keyword. If you're dealing with interfaces, use the implements keyword. Where is this one? It's in code objects. Code objects. Yep, implements shape. And then it will yell at me an error. What's the error say? I have to implement the methods that I got from shape. So it says that I have implemented a getPerimeter method. So let's go ahead and write a getPerimeter method. Public double get perimeter, and now I'll return get circumference because it's the same thing. So we've implemented that method, and now we've implemented also the get area method that we have to say that we need to be able to say that we qualified as a shape. Now let's look at the same thing for a triangle shape. A triangle implements shape, and as soon as we say it implements, it says that we have to either implement those methods or we need to become abstract. So let's go ahead and implement those methods. So we've overridden them. So now let's go ahead and they give us the wrong answers, but we've implemented them, and now we can say we're a shape. So let's go ahead and actually, write a triangle method in the 10 minutes we have left. A triangle. So let's go ahead and say, so a triangle is defined by three things. You can either define it by the angles and the sides, and most people find it easier to deal with angles. So let's go ahead, not angles, with the sides. So let's say private double A, private double B, private double C. All right, so getting the perimeter for a triangle is pretty easy. You just add together A, B, and C. Let's also make a constructor. So public triangle takes in double A, double B, double C. Okay. So we've got ourselves a triangle here with three sides, and we will say this dot A is equal to the A that's passed in, this dot B is equal to B that's passed in, this dot C is equal to C that's passed in. All right. So now to get the area, well, that's a bit more complicated without having the angles, right? Normally area for a triangle, the way you've learned how to do it is 1/2 base times height. But if you don't have base and height, right? You only have the three sides, so we need a different equation. And the equation is this: double S is equal to 0.5. I think it's well, it's in the slides. 0.5 A plus times A plus B plus C, and then to compute the area of the triangle, you do math dot square root S times S minus A times S minus B times S minus C. And that's the equation for an area, and I only learned it when I've given this on an exam before, where I give you that formula, and I've only learned that when I had to write this up. Okay, so we can implement shapes like this. When we get back on Monday, I'll talk more about this. But for the last 7 minutes, what I'm going to do is I'm going to talk about your homework in a bit more detail, the homework that I'm going to give out on Friday. Okay, so the homework that I'm going to give out on Friday is the game of life. Not the spinny game, but Conway's game of life. A 0-player game. Not this game, but Conway's game of life. Oh, and look at that. It started playing it on my Google browser. Or sorry, my Google window. It's hard to see because it's a bit light colored, but let's take a look at it. So Conway's game of life is fairly straightforward. It takes place in a grid, okay? And the rules are pretty simple. It goes by in turns and in steps, okay? It's made up of cells, and cells are either alive or dead. So, if you have, and it works like this: if you have 2 or 3 neighbors, you stay alive. So let's focus on this grid. These guys all of these guys have 3 neighbors. A neighbor being defined as one of the 8 squares around you. Okay? So each grid has 2 or 3 neighbors. Sorry. Each square can have up to 8 neighbors, right? And if you have less than 2 or 3 neighbors, you die of loneliness. That's it. Okay, so let me just zoom in. So let's look at this. So we go to the next step, right? We see that that all the neighbors and all the guys in this square have survived, but all the single dots who had no neighbors, they died of loneliness. Okay, so if you have 2 or 3 neighbors, you're perfectly happy. Rule 2: if you have more than 3 neighbors, so 4 or more neighbors, you die of overcrowding. So let's go ahead and see what happens here. So notice that those guys get deleted. And then the third rule is, if you're a dead cell and you have exactly 3 neighbors, you come back to life. So you stay alive if you have 2 or 3 neighbors, and you come back to life if you have exactly 3 neighbors. So let's look at this thing over here. So for the next step, he has only 1 neighbor. He's going to die. He has 2 neighbors. He'll stay alive. He has 1 neighbor. He's going to die. But this square and this square have exactly 3 neighbors. So they're going to come back to life. So next step, it flips like that. And now, same thing happens here. These two guys have only one neighbor, so those live cells become dead. But these have exactly 3 neighbors, so they come to life. And so it stays in this kind of steady state. Now, this one is going to stay in a steady state because, of course, it's just going to stay alive. Another, all of them have exactly 3 neighbors. A similar pattern is over here. Each of these guys has exactly 2 neighbors. So it's going to stay in a steady state. Now, what makes this interesting is that steady states are boring. But if we let this run and generate, we see that there's this little thing that we started with. It's called a glider because it essentially goes through the same 4 patterns over and over again, and it slowly glides across the screen. So let's go ahead and look at an exploder. And what happens with these things is that they generate, just using these basic rules of cells being alive or dead, they generate these very interesting patterns. Right? And it's an open question as to whether these things end or not. And notice how it's got into a kind of an oscillation here where it's just doing the same thing again. Now this has been a game for a while. So this is something called the Gosper glider gun. And what this is that this is a starting pattern that somebody figured out that essentially creates gliders. Now it might have been your instinct that basically these things come into a solid state and eventually stop. But what happens is that these patterns create gliders. So it's a very interesting thing, and it creates programs. It creates very interesting just patterns. So your assignment is essentially to recreate this game. Now, you don't have to do it with graphics. Instead, you're going to use an array and print the array to do that using cells, different one character to say that the cell is dead and one character to say the cell is alive. You can program it with graphics if you want to. The hard part is a bit of the logic. Because the logic, to tell whether a cell is alive or dead, you have to check, it's different once you get to the corners, right? If you're in the corner, you got to check only these 3 squares and these guys are out of bounds. Or if you're on the side, you have to worry about being out of bounds. But Conway's Game of Life is pretty much, you've got a Wikipedia article about it. It's very well detailed. I have a very extensive write-up on this one. But this one is a very fun lab that students really enjoy. All right, so that's it for today's lecture. I'll see you on Friday.